Continue our discussion of inverse functions. In our previous class on inverse functions, we learned that the range of f is the domain of f inverse, and the domain of f is the range of f inverse. Right, so here's a little picture that describes it. This circle that has a in it, this is the domain of f, and f takes a and sends it to an input of a and gives an output of b, and it sends it to the range, right? So we have the domain and the range of f. But f inverse reverses, right? F inverse takes the outputs of f as its inputs and sends them backwards. So that means that the range of f inverse, the set of outputs, was the domain of f. Right, and to verify that f and g are inverses of each other, you take the composition of the two functions and you should get x. Right, so many actions are reversible. For example, how would you describe the inverse or the undo of put on your socks and then put on your shoe? Right, how do you undo putting on your socks and putting on your shoes? Take off your shoes, then take off your socks, right? So many actions can be undone. And so my actions are put on socks first, right? Then put on shoes. So to undo, I have to undo it in the reverse order that I did it, right? So first thing I have to do is take off shoes and then take off socks. Okay. So similarly, undoing operations in mathematics, to get back to where you started, to make a round trip, is the idea associated with inverse functions. So we're going to follow the same procedure as above, and we're going to undo or find the inverse of the following operations, right? So if I subtract 9 from x and then multiply the result by 5, so first I'm going to subtract 9 and then multiply by 5. So to undo, to get the x back, I have to undo what I did in the reverse order that I did it, right? So first I subtracted 9, and then I multiplied by 5. So to undo, what should I do? Divide by 5. Yep, so first I would divide by 5, and then I would add 9. Right, so you have to use the inverse operation, and you have to undo in the reverse order that you did it. Okay, so the next question that arises is whether or not every function has an inverse. We talked about this a little bit in class 21, right? We learned that the function that associated female literacy rate with a particular nation didn't produce a function when we swapped inputs and outputs, right? Because there were two nations that had a 99% literacy rate, so that made it not a function. So to answer this question about whether or not every function has an inverse, let's look at two functions, x plus 1, f of x is x plus 1, and g of x is x minus 1 squared. So here are 4 possible solutions for the f of x function. These are just 4 points that are on the line f of x equals x plus 1. Right? If I put in a negative 2 for x, I get negative 1 for y. Put in a negative 1 for x, I get 0 for y. So these are just 4 points on the graph of f. Now, if I swap the inputs and outputs, right, just change them around, that gives me the inverse. That is the inverse of f. So for the function f of x equals x plus 1, different inputs produce different outputs. So that means that the inverse is a function, right? So if I look at this inverse, I never have an output producing I never have an input producing two different outputs. So this is a function. Okay, so this function f, its inverse is also a function. But when I look at g, here's a function g, x minus 1 squared. These are just 4 points that are on the graph of g, and I got them randomly. I just plugged some x values into g and got the y values. So for example, negative 2. If I put negative 2 in here, I get negative 2 minus 1 is negative 3. Square it, you get 9. That means negative 2, 9 is on the graph. So these are 4 points on the graph of g. And g is a function because it passes the vertical line test, right? So parabola passes vertical line test. So this is a function. G itself is a function. But when I swap the inputs and the outputs to look at the inverse, what can you say about that set of x's and y's? Yeah, I have 4 as an input, and it produces 2 different outputs. First, it gives me a -1, and then it gives me a 3. So that means that this is not a function. Because so if I wanted to know, if I asked g of 4, you know, what is that? It can only have one answer. To be a function, it can only have one answer, but it has 2 values. You get 2 different values, which makes it not a function. Okay, so for the function, certain inputs produce the same output. Certain inputs produce different outputs. That is the problem. This is a typo. Oh, no. Sorry. We're talking about g, the original function g. Certain inputs produce the same output, so that when I reverse them, it's not a function. Okay. So that means that the inverse of g is not a function. All right, so when we swapped the inputs and the outputs for our functions f and g, we noted that the inverse of the linear function is a function, but the inverse of the quadratic function is not a function. So can we look at the graph of a function and tell if it has an inverse? We actually talked about this last class, right? So yes, we can. If you draw a horizontal line at the line y = 4, which is right here, okay, how many times does the line intersect the graph of f? Once, because f is just the line. Once. But how many times does the line intersect the graph of g? Twice. Right? So that means that an input of -1 or an input of 2 both produce an output of 4. So when I swap inputs and outputs, I'm going to have 4 producing 2 different outputs, not a function. So if any horizontal line, such as the one we just drew, intersects a graph at 2 or more points, then the graph of the function does not have an inverse function. So we refer to this visual test as the horizontal line test, or HLT. And it just says a function f has an inverse that is a function, f inverse, if there is no horizontal line that intersects the graph of the function f at more than 1 point. So which of these 2 graphs represents, first of all, are both of these graphs functions themselves? Not talking about the inverses. Yes, because you use the vertical line test, right? So that's a function, and that's a function, vertical line test. Right, so they're both functions, but one of them has an inverse that is also a function, and one of them does not. Which one has an inverse that is a function? B, because B also passes the horizontal line test. Sweep a horizontal line through here, and it never intersects more than once. So in this one, the inverse of f of x is a function, right? This passes HLT. Okay, but A does not pass HLT, right? You can draw a horizontal line and it will intersect in several places. So this one fails HLT, which means the inverse of the function is not a function. It has an inverse that is not a function itself. So a function passes the horizontal line test if this condition is met, and this is just sort of a fancy algebraic way of saying, of writing the horizontal line test. So this says if you have 2 different x's, if x1 and x2 are different, then the y values have to be different. So if you have 2 different x values, the y values have to be different. So if we look at this picture, so this looks like 1 and 3, right? Those are two different x values, but their y value is the same, right? So that's what makes it fail HLT. So 1 to 2, yeah, or 2 to 1, 2 to 1. Two x's go to one y, so it's 2 to 1. All right, so such a function is called 1-to-1, a function that passes the horizontal line test where different x's always produce different y's. We call that kind of a function 1-to-1. Yeah, Tenzin. Yeah. Then its inverse is not a function. Yes. So this graph here, this graph, is a function because it passes the vertical line test, right? We learned that several weeks ago. So this is a function. But then I do the horizontal line test and it fails, right? It crosses in more than one spot, which means that the inverse of this guy is not a function. All right, let's take a look at how to find the inverse of a function algebraically. So if a function is defined by an equation, then we can obtain an equation for f inverse by interchanging the role of x and y in the function, and then solving for y. So your textbook refers to this procedure as the switch and solve strategy. Switch the x's and y's and then solve for y. So for example, here's a function f of x equals 5x minus 6. I want to find a formula for its inverse. All right, so step 1, replace f of x with a y. So we write y equals 5x minus 6. Step 2, interchange x and y. Replace all your y's with x's and all your x's with y's. So this now says x equals 5y minus 6. Because that's what inverse functions do, right? They just change the role of input and output. So we swap the x's and y's. Step 3 is solve for y. Okay. If this equation doesn't define y as a function of x, then f does not have an inverse function and we stop here. But in this case, we can solve for y as a function of x, no problem. How about after I finish this, I'll show you one. Okay. So if I wanted to solve this thing for y, I would add 6 to both sides and then divide both sides by 5. So my next step 3 here would be y equals x minus 6 over 5. And then step 4 is to just replace the y in step 3 with an f inverse of x. And I now have a formula for the function that is the inverse of f. And I can verify that that is actually the inverse by composing, right? Compose f and f inverse to check your work. So f of x is 5x minus 6. So I want to do f composed with f inverse of x. Okay. Yeah, Tony. Yes, thank you. That was a silly mistake. Plus. Though I would have found it when I was doing this composition because it would not have come out as x and I would have realized I made a mistake. All right, so f composed with f inverse of x. So f is a machine, right, where whatever you put in, it does 5 times it and subtracts 6, right? So when you drop in an x, it does 5x minus 6. If I dropped in a smiley face, it would do 5 times a smiley face minus 6. So I'm going to drop in to my f machine an f inverse of x. So this is going to become 5 times f inverse of x minus 6. But f inverse has a formula that we just figured out, x plus 6 over 5. So this says 5. Replace f inverse with its formula, x plus 6 over 5 minus 6. And now I just want to simplify this expression. I have 5 times something divided by 5. 5 and divided by 5 undo each other, so those cancel. And then I have x plus 6 minus 6, and that is x. So I compose them, and I got x back, so I know my answer is right. Yes, always comes out to x. If it comes out to something other than x, then you did it wrong. Yep. All right, you really should also do the composition in the other order, but I don't really feel like it. So I'm just going to write it down. I'm just going to write f inverse of f of x should also come out to x. I do the composition in the other order. Check. Okay, so now, Katrina, you asked me what's an example of a function where of a stopping point? Yeah. No. But a function that would show that might be y equals x squared plus 1. Actually, I should call it f of x. F of x equals x squared plus 1. So graphically, x squared plus 1 looks like that, right? Does that function have an inverse that is also a function? No, not according to the horizontal line test, right? So if I do my algebraic procedure, I'm expecting to run into a roadblock, right? So let's see what happens. My algebraic procedure is replace f of x with y, swap x's and y's, and then solve for y. So subtract 1 from both sides, and then what do I do? Square root both sides. And that means I end up with y equals plus or minus the square root of x minus 1. And now y is not a function of x, because for any input x, I'm going to get two outputs, a positive one and a negative one. So this equation is not a function. Any input will give me two different outputs, a positive and a negative. Make sense? Okay. Sure. All right, so now that we've done a linear example, and we just did an example of finding an inverse, it just didn't happen to also be a function. Why don't you guys try finding the inverse of f of x equals x cubed plus 1? So my four-step procedure, first, rewrite f of x as a y. So I have y equals x cubed plus 1. Step 2, make x's y's and y's x's. So I'm going to have x equals y cubed plus 1. Step 3, solve for y. So I'm going to subtract 1 from both sides. So I have y cubed equals x minus 1. And then to get the y by itself, to undo cubing, you cube root. So I'm going to take the cube root of both sides. Cube root, cube root. The cube root of y cubed is y. And the cube root of x minus 1 is just the cube root of x minus 1. When you have an odd root, you don't have to do the plus or minus, right? Odd, don't modify. Okay, so we just get the cube root of x minus 1. So this is a function because we don't have, because the plus or minus doesn't pop up to ruin it. And if we were to graph x cubed plus 1, it looks like that, something like that, which will pass the horizontal line test. So we know that this actually is a function. We have confirmed it 2 ways, algebraically and graphically. That it passes HLT and that then y is a function of x is enough to say that this is a function. If you really want to prove that your answer is right, we should show that f composed with f inverse of x equals x, right? So we should check it. So let's do it. Thank you for reminding me. All right, so this is my f inverse. So f is a function that cubes things and adds 1. But instead of an x into the function, I'm going to put in an f inverse. So this is going to be f inverse of x cubed plus 1. That's f of f inverse of x, right? Does that equal x? Well, save a little room here. Okay, f inverse has a formula that I just found, and I'm going to replace f inverse of x with its formula. So this is just a little substitution, and the formula for f inverse is the cube root of x minus 1, and I'm going to cube that and add 1. So when you have a cube root cubed, those things cancel, right? My cube root and my cube cancel, so I get x minus 1, just what's under the radical, plus 1, which is x. So I composed them, and I got x, so I know my answer is right. Is that okay? All right. So if I want to sketch the graph of an inverse function, instead of finding an explicit formula, right? This is a step-by-step procedure. I can find a formula. But if all I had was a graph to look at, and I wanted to draw a graph of its inverse, right? Because the coordinates of the ordered pairs of f inverse are the ordered pairs of f, but with the coordinates reversed, I can use the coordinates to create a graph of f inverse just by picking a few key points and swapping the x and the y coordinate. So here's a graph of f. I have it sketched here. Let's list a few nice points on the graph of f. 0, 1. It goes right through 0, 1. Some other nice points? 1, 2. Ooh, it's not quite, it doesn't ever actually touch the x-axis. Yes. 3, 9. 3, 9. Yep. Yeah. 3, 8. Okay. 3, 8. Yep. Thank you. All right, that's good. 4 points. Let's the corresponding points on the graph of f inverse are just the x and y coordinates swapped. That's what inverse functions do. Swap input and output. So I have 1, 0, 2, 1, 4, 2, 8, 3. I'm going to plot these new points on the coordinate plane, connect them with a nice smooth curve, and see the result. So 1, 0 is here. 2, 1, 4, 2, and 8, 3. It's going to look like that. And maybe I'm going to add just like one negative up here, like -1. What's my y coordinate on f when x is -1? Looks like about a half. Yeah. So that means I have a half -1 on the graph of f inverse, which is here. And that tells me, oh, okay, go like this. So what do you notice about the graph of f and the graph of f inverse? They're both functions. Yes, that's true. They are a reflection, yeah. It's not origin symmetry. It's that diagonal line y equals x, that diagonal line that I have drawn in there. That's like the mirror. That's the line of symmetry, the line y equals x. So the graph of a function and the graph of its inverse are symmetric about the line y equals x. And if the graph were folded along that line, the graph of f would lie on top of the graph of inverse of the inverse. So it doesn't have a special name, no. So if you want to sketch the graph of a function's inverse, you can picture a reflection over the line y equals x and sketch it. Some people are really good at visualizing this. Or pick a few key points, swap the x and y coordinates, and that will give you the same result. That will cause a reflection over the line y equals x. All right, so here's a graph of a function f of x, just a little piecewise function. I want you to sketch the graph of the inverse. All right, let's take a look at it. So -3, -2 is a point on f. So what is the corresponding point on f inverse? -2, -3. We just swap the x and the y. This can get confusing because when we did symmetry earlier, we made things negative. Or took the opposite of things. So here, the signs always just stay the same. You just swap them. So -2, -3 is a graph on the inverse function. All right, so -1, 0 is a point on f. What is the corresponding point on f inverse? Great, 0, -1. And 4, 2, corresponding point would be 2, 4. Right, and so then I can just connect those. And does it look like they are symmetric over the line y equals x? Yes. I could draw that line in just to make sure. Yeah, I definitely look like a mirror over the line y equals x. You're right. I don't think of it. Let's try it just for fun. I want to make a dashed line that's pink. It is. Yeah, I'll have to play around with the settings. I don't feel like doing it right now. Okay, so let's talk about if we want to find the inverse of a function that has a restricted domain. So earlier in class, earlier today, we said if I want to find the inverse of f of x equals x squared plus 1, but x squared would come out the same, I can't. The inverse is not a function, right? So, and that is because it doesn't pass the horizontal line test, right? So here's a graph of x squared. Sorry, this is supposed to be -1 to match the graph x squared -1. So if you look at this graph and you try to run a horizontal line through it, it hits in many different places twice, right? So f of x equals x squared -1, its inverse is not a function. But if I restrict the domain, if I say, well, if I only look at the right-hand side of the graph and ignore this, that piece of the function has an inverse, right? So if I say, I'm going to look at f of x equals x squared -1, but only for x's to the right of 0. Okay, so this is a function that I have defined. It equals x squared -1, but its domain is only positive x's. Can't plug negative x's in. I just decided, right? You feel like I feel like I'm getting looks like, why would you do that? Because I wanted to, right? I wanted this function to have an inverse, and in order to make it pass the horizontal line test, I had to get rid of half of it. Okay. So I said, well, I'm going to keep the positive half because I don't like dealing with negatives, right? So I'm just going to keep the right-hand side of x squared. So once the left-hand side is gone, now it passes the horizontal line test, and I can find its inverse, right? So I say, okay, then y equals x squared minus 1. Swap the x's and the y's. Solve for y. Y squared equals x minus 1. And y equals the square root of x minus 1. Yeah, thank you. Plus 1. And this time I don't have to put a plus or a minus because why? Yeah, because I'm only doing the positive x's, right? So if x is strictly positive, this is my domain of f. That means that it is my range of f inverse, which means that the y's of f inverse are only going to be positive. So I don't have to put the negative thing there. So this is my f inverse of x. Its range is only positives, right? So if I restrict the domain of f to positives, then that would be the range of f inverse, and I don't have to put the plus or the minus. It's just the plus. And if I sketch them, right, this is the graph of x squared minus 1, just the right-hand side, right? So I've restricted the domain so that I only graphed x's that are positive. And when I graph the square root of x plus 1, that's the graph of the square root of x shifted left 1, right? And I get the nice perfect symmetry. And I don't have the other half of x squared messing up my picture. Yes, yes, that's a great question. Okay, so let's look at, what if I had chosen the other half of the graph, right? So if I graph the right half and the left half, this is the graph of f of x equals x squared minus 1, right? So if instead of restricting the domain to positive x values to the right-hand side of the graph, what if I said, actually, let's get rid of this half? Now it passes HLT, right? All right, so my new function f, I'm going to define as f of x equals x squared minus 1, but I'm going to restrict x's to the left side of 0. Okay. So now let's see, what do we come up with if I try to figure out what f inverse is? Y equals x squared minus 1. And this x less than or equal to 0, this is the domain of f, which means it's the range of f inverse, right? So my outputs for f inverse have to be negative because my inputs for f are all negative. All right, so I solve this thing for, swap the x's and y's. Solve this thing for y, and I get y equals x plus 1 square rooted, but I get negative ones, right? This time I'm only going to take the negative ones because I know that my range has to be only negatives, because the range of f inverse has to be the domain of f, which is only negatives. So this is the inverse function of x squared minus 1 if you restrict the domain to the other half. And that looks like the square root of x shifted left 1 and reflected over the x-axis, right? So square root x shifted left 1, reflected over the x-axis. So that would look like Am I doing this right? Like that? Yeah. And if I draw the line y equals x, it does look like a reflection. That was a great question. Thank you. All right, so now I have some work for you to work on in your groups. For each of these questions, I've given you a formula and a graph of a function f, and I want you to determine if the function's 1-to-1, so you can tell by the HLT. And then if it is 1-to-1, sketch its inverse just by picking some key points, swapping x and y coordinates. And then finally, if it's possible, find an equation for f inverse by doing our swap and solve strategy. And don't try to actually do this for 5, 6, 7, and 8 because we don't have the algebraic tools to do those algebraically. So 1 through 4, do part 3, and then drop part 3 for 5 through 8.